Good morning students. In this video, I am going to explain image smoothing techniques and image sharpening techniques in frequency domain. So we have seen same topic image smoothing and image sharpening techniques in the spatial domain. So now we concentrate on those techniques in frequency domain for the given image. Now we have seen in the previous video here how can you enhance the image by using this frequency domain. And now coming to the different techniques in frequency domain. The first one is image smoothing techniques. So okay, here image smoothing is nothing but image what is that? We are using here low pass filtering action to the image. So now here low pass filtering means which allows the low frequency components and attenuates the high frequency components. High frequency components resembles the here sudden transitions or edges. Low frequency components resembles the smooth area, smooth surface in the image. So now here image smoothing means you just remove the noise which are occurred due to the sudden transitions, sudden transition intensity values, and then and hence you can get the image smoothing, so that may appear like a blurred image. Okay, now here is a different low pass filters to do this image smoothing in the frequency domain. The first one is nothing but ideal low pass filter. Next one, Butterworth low pass filter. Next one, Gaussian low pass filter. So see here the first one, ideal low pass filter. So ideal low pass filter transfer function is here h of u comma v, that is equal to 1 for d of u comma v less than or equal to d naught, 0 for d of u comma v greater than d naught. This is the ideal low pass filter transfer function. So our system function, so we are using here one system. So in that system we just pass the image, that is the frequency domain image. So here the representation is f of u comma v. Then the system output is nothing but the multiplication between frequency domain representation of h of u comma v and f of u comma v. So that is nothing but g of u comma v enhanced image. G of u comma v is equal to f of u comma v into h of u comma v. So then you can get the enhanced image based on this h of u comma v. Then you can again apply the inverse Fourier transform on the g of u comma v. Then you can get the g of x comma y, that is the enhanced image of the f of x comma y. So all these we already discussed in the previous video. So now concentrate on the system transfer functions. Here the system is ideal low pass filter, so that nature should be like this. Okay, here d of u comma v is nothing but distance from u comma v to the center of the mask. So here d naught represents the radius, right? So now here if you observe, so these are nothing but representation of the h of u comma v, so in different ways. So the first one is nothing but here the h of u comma v with respect to the u comma v, right? So okay, see here based on u comma v, based on, right? So these are the independent variables u comma v, right? Here the intensity levels of h of u comma v are like this. Okay, so here see this, here at lower, at a particular lower, that means u0 v0, right? So that means the origin position. So here near the origin we have the higher intensities. So here as uv goes on increasing, so the intensity levels are here 0, right? So that means here is a abrupt change from higher intensity. What is that? Higher intensity to the lower intensity. So okay, here this is the one. What is the nature of the h of u comma v according to this one? So okay, here this is nothing but filter displayed as an image. This is nothing but a plot of an ideal low pass filter transfer function. So this is nothing but filter radial cross section. So now here if you see the particular thing, so this one, so here we can see like this, okay, this one, right? So see this one is let it be v direction, this one is the u direction. So of course you know that, so here is a particular thing, what is that? Origin position. Instead of here we are using the origin position here. You know that since here we are shifting the total image from the 0 comma 0 to the center of the particular image, okay, right? So here, why here? To store the most of the information at the center, not at the corners, okay. We have the discussion on this also in the previous video, okay. That's why here consider this one, right? So center, here the origin is at the center position of the particular image. So now here if you observe, so here with the radius, what is that? D naught, with the radius D naught, so okay, you have the value 1. You have the value 1. 1 represents white, 0 represents black. That's why d of u comma v less than or equal to d naught, then the value is 1. d of u comma v greater than d naught, then the value is 0. d of u comma v means this one, okay, right? Here the d naught is this one, okay, right? That means the radius of this d of u comma v, okay. The whole thing is h of u comma v, but where the intensity values are at high, that is nothing but d of u comma v. This whiteness is nothing but that one is represented as d of u comma v, okay. Now here this one is the image to represent the h of u comma v. This is the plot or graph between the h of u comma v u and u comma v. Now coming to this one here, if I plot h of u comma v to the d of u comma v, right? So here if d of u comma v is d naught, right? So up to the d naught the values are high, the values are at high. So at greater than d naught the values are 0. h of u comma v values are 0. That's why here this is the plot between h of u comma v to the d of u comma v. Okay, so now here you should draw all these figures in the exam, and then you should mention the equation also. Okay, this equation, right? So here ideal case, this is this particular graph. So observe this graph. So here you can see the, what is that? Sudden change from higher intensity to the lower intensity, okay, at d naught, right? So okay, here so there is a abrupt change from higher value to the lower value. So this one is the ideal low pass filter case, okay. So okay, now here examples. Say this is the input image, so that is a spatial domain image. You should enhance this image, okay. So that too image smoothing. What is the image smoothing here? So here it removes the sudden transitions, or it reduces the sudden sharp transitions effect, and okay, and hence removes the noise, okay. In such a way you can get the blurriness in the image, okay. Now here if you observe, this is the image with the size 500 by 500 pixels, okay, and this is nothing but this Fourier spectrum. So okay, what is this? Frequency domain representation of this image is nothing but this one. So don't consider this what is that rings, right? So right, consider only the this one, okay. Don't consider these rings, okay. These are nothing but the what is that with some radius, right? So we or we just drawn the circles here to represent d of u comma v or d naught. It's okay. This is the Fourier spectrum, and just this is the superimposed circles have radii values of 5, 15, 30, 80, 230. Okay, so that means here see this is the circle with the radius 5, this is the 15, next one 30, next one 80, and next one is the 230. Okay, so that means here if I take the 5 radius, so that has the 92% of the image power. Okay, right? So see this here, if I take the only the radius 5, with that only I can get the 92% of the total particular image power. Okay, if I take 15, right, so 94.6 is the total image power in that particular only. Okay, if I eliminate the other than the radius, what is that, 15, then of course I can get the 94.6 percentage. What it means here, that means so here most of the energy is stored in the, what is that, low frequency region. Okay, that's why it's okay. Now with the radius 30, so you can get the 96.4 percentage of the power. So here 80 means 98 percentage, 230 means this one. Okay, so that is 99.5% of the image power. Okay, so here smaller the d naught, more high frequency components are removed. Am I correct? So if smaller the d naught, right? So if I take this d naught is smaller, these are the high frequency components, right? So high frequency components, so these are eliminated. Am I correct? So why here, if I multiply this h of u comma v to the image frequency domain, what is that, f of u comma v, then I can get the resultant image, what is that, g of u comma v. So that means here here the radius d naught, so here d of u comma v less than or equal to d naught, this one is the 1, so 1 is multiplied by the f of u comma v, then you can get the f of u comma v. That means here in this position, in this particular what is that, at higher intensities or at white level, then you can get the image as it is. But apart from, what is that, if d of u comma v greater than d naught, other than this range d naught, that means the blackness is there. So in this region, if I multiply this h of u comma v to the f of u comma v to get the g of u comma v, that means here the value is 0, 0 into anything 0. That means here the g of u comma v also 0 for greater than d naught. So this is the one here. That means if I pass the input image through this ideal low pass filter, so I can get the image. What is that? So in that, higher frequency components are removed and it has only lower frequency component. That range depends on the, what is that, d naught. If d naught is very small, right, so more number of high frequency components are removed. So that is the one here. So now here, so here these are the results of ideal low pass filter. So this is the input image, right? So now if I apply this image to the ideal low pass filter, so then the output is, right, so the output image in the spatial domain. Okay, right? So actually in the back end, what is the procedure? This one is converted into the frequency domain. Now the filter also in the frequency domain. Now these two are multiplied and then you can get the multiplied output, and then again apply the inverse transformation technique, and then you can get the one image. So this is the one. This is f of u comma v. This is g of u comma v with the filter radius. What is that? 5. Okay, right. If the filter radius is 5, the output is this one. If the filter radius is 15, this one, 30, this one, 80, this one. What is the next one? 230. 230, this one. So that means if you observe this one, if the radius is large, right, you can see the your image as it is. There is no much variation between these two. That means here there are much number of what is that? There are no much number of higher frequency components to remove here. Okay, so these two are similar. If I consider this one, the radius 5 means beyond the 5, all the values are eliminated. Then I can get the image like this. Okay, right? So it's a totally blurred. Okay, I cannot see the but my original image here. Am I correct? So now if I see the next level, what is that with the radius 15? So image like this. If the radius is next one, what is that? 30. See this. 80, this one. Okay, like that. That means based on the radius d naught value of the particular filter, so we can get the, what is that, enhanced images, image smoothing. Okay, right. So based on the application, we just decide the d naught value. Okay, now if you observe this one in the particular output images or enhanced images or image smoothening image what is that, smoothened images, then you can observe the ringing effects. See this. Okay, why these are here, why what is the cause here, here we will see that one here. Okay, so here observe. So we can easily remove the noise, right? So and then that means which reduces the sudden transition intensities here. Okay, sharp transitions effect. And here that the enhance, that one is removed the, what is that, noise. And here, but it that means now some ringing effect is here appeared. Okay, so that's why here what is the reason here for this ringing effect, we will see here. Okay, so if you observe the particular what is that, h of u comma v, so here the transfer function, so this one is nothing but with d naught is equal to 5, right? So this is the graph between the h of u comma v and u of u comma v. Okay, so this one, that means there is a sudden change in the amplitude. Okay, now so here if you observe the spatial response of ideal low pass filter with d naught 5, so this one is 1, right, frequency domain image for the ideal low pass filter with d naught 5. If I apply the inverse transformation technique on that, I can get the, so right, spatial domain image like this. Okay, see this. So this is the spatial domain image for the ideal low pass filter with d naught 5. If I observe the here, what is that, this particular h of x comma y, let it be h of x comma y, h of x comma y with the x comma y plot, then so I can observe the, right, what is that, ripples here, what is that, ripples, right? So here, so this is the graph between the h of x comma y to the x comma y. So for this particular, right, so h of u comma v, the graph for the h of x comma y is like this. Okay, see this. So here you may observe the some ripples. Okay, right. Due to these ripples, right, so you can observe the, what is that, ringing effect in the image, enhanced image. Okay, right. So here observe. So this is the one here, frequency domain. What is that, inverse low pass filter of radius. What is that, ideal low pass filter of radius 5. Ideal low pass filter of radius 5. So now here, this one is nothing but the, if it is h of u comma v, this is nothing but here h of x comma y. Okay, corresponding spatial filter, this one. So okay, and then this is the graph h of x comma y with respect to the x comma y. So this is nothing but what is this? H of x comma y image. Okay, so this is the one I just drawn 1D case here for the h of x comma y. It's okay. Now here coming to the here one image. So with which is having 5 pixels only, one image like f of x comma y. So now here if I convolve these two, right, f of x comma y, and this one is nothing but h of x comma y. This is h of u comma v, this is h of x comma y, this is f of x comma y. So here if I convert f of x comma y to the h of x comma y, then I can get the image like this. See this, right? So that means here due to the ripples you may see the what is that ringing effect in the h of x comma y for the h of u comma v. So now due to this, so if I take the image with simply 5 pixels, so at each particular pixel, right, so that means with the intensity 1, so if you observe, so here you can see the ringing effect. Okay, right? So here after convolving these two, you can get the image like this. Okay, right? So this is nothing but the what is that enhanced image of this one. So right? So this is the input image, this is the filter representing the image. So I just convolve these two, then I can get the image like this in the spatial domain. Okay, right? It's okay. So due to this, right, what is that ringing effect? So that is caused by the ripples in the particular spatial domain representation of the ideal low pass filter. Okay, right? So to reduce that ringing effect, here we can go to the another technique. What is that? Butterworth low pass filter and also Gaussian low pass filter. Coming to the next one, Butterworth low pass filter. The transfer function is here h of u comma v is equal to 1 by 1 plus d of u comma v by d naught whole power 2n, where n is the filter order, d naught is the cutoff frequency or radius. Okay, now here observe here the different plots here. The first one is nothing but h of u comma v with respect to u comma v, right? It's a graph. Observe here there is no abrupt change here from higher intensity to lower intensity. So now there is a smooth variation. So see this, so like this. And then now due to this here, that means the value is reduced from 1 to 0 slowly. So that's why here whiteness is slowly converted to the blackness. The values are here different. Next one 0.9, 0.8, 0.7, 0.6 like that, and then goes to the 0. That's why here some variation. Okay, observe this variation. This is the image for the Butterworth low pass filter in frequency domain. Now here the graph between h of u comma v and d of u comma v. Okay, right? So if d naught is here now, so with the order n1, the response like this, n2, n3, n4. Okay, based on the order, you can get the variation. So different slopes in the particular characteristic. Okay, so observe this one. Okay, so now here coming to the here example. So here same image with the same d naught values like 5, 15, 30, 80, 230 with the order 2 here. I am taking Butterworth low pass filter. The order n is here 2. Now observe here. So you just compare this image with the previous image. So this one. Okay, so here is the one with the results with the ideal low pass filter. Now coming to this one. So results with the Butterworth low pass filter. So here observe here with the particular radius 5. In the previous case we did not see anything, okay, in the image. Okay, but now see here is a small you can observe particular thing. It's a better image when compared with the previous one. Okay, now observe, is there any ringing effect? Okay, so very much less. Okay, less ringing effect compared to the ideal low pass filter. Okay, so now here coming to the here For this radius, right? So what is that? These are nothing but a spatial domain representation of the low pass filters. Okay, we have seen the what is that h of u comma v. Now what is h of x comma y for the particular system or filter. So here spatial representation of Butterworth low pass filters of order 1, 2, 5 and 10 and corresponding gray level profiles through the center of the filters. So here the if order n is equal to 1, so now the image, what is that? Image should be like this. Now the graph, observe the graph also, there is no ripples here. If order 2, see this order 5, order 20, that means if the order is increased, n value, so n value is increased, so here you can observe the ripples in the particular, what is that characteristic, then you can get the ringing. That means if the filter order is increased, ringing effect also increased. Okay, so now you have seen this example with the order 2, with order 2, that's why here you can so see this is the one characteristic, so there is a less number of ripples, that's why you did not get the ripples here. Okay, right. Okay, if the order is here increased, right, then you can observe the ripples also here, same as in the ideal low pass filter. Coming to the next one, Gaussian low pass filter. Gaussian low pass filter. So here the transfer function is h of u comma v is equal to e power minus d square of u comma v by 2 d naught square. So here let it consider d naught is the radius or spread factor. Okay, now here observe a graph. So almost similar to Butterworth, but small variation is there. Observe. Okay, now here this one is the image, right? So for the filter, and this is the graph between h of u comma v and d of u comma v. So here for d naught 10, 20, 40, 100. So graph is like this, characteristic curves are like this. So now here Gaussian filter is the only filter that has no ripple and hence no ringing effect. So due to this nature, if I get h of x comma y from this h of u comma v, right, there are no ripples in the particular h of x comma y. So based on this nature, okay, right, now if observe the here Gaussian low pass filter with the d naught 5. This is nothing but the h of x comma y for the h of u comma v. So observe this one. Okay. So here are no ripples in this. Okay. So smooth surface. What is that? Flat surface. Okay. Now here same example with the same radii values. So 5, 15, 30, 80, 230. Okay. Observe this. So there is no ringing effect. Okay, right? So and then you can smooth the image with the different radius values of the filter, Gaussian low pass filter. Okay, so there is the one here. Next application here, just to take one sample text of a poor resolution. Observe here broken characteristics in magnified view also. So if I apply Gaussian low pass filter to this text, so I can get the image like this. So see this here. So how I get the, what is that, better looking image. Okay, see this. Okay, right. So broken character segments were joined. Observe here. Okay, right. So that means here this Gaussian low pass filter can be used to remove jagged edges and repair broken characters. Okay, so that means here is a sudden transition. So that is a smooth end. Then you can get the image like this. Okay, right. So now here observe this one, another example. So that removes the wrinkles here. See this here. If you observe, wrinkles are there. So if I apply the Gaussian low pass filter, so the first one is the 1028 by 732 pixels original image. So GLPF Gaussian low pass filter with the D naught 100. Okay, there is the one. With the D naught 80, this is the output. Okay, right. So okay, here Observe here the skin lines are reduced, okay, which removes the wrinkles here, okay, right? So here this is an example for the Gaussian low pass filter. Okay, now image sharpening techniques in frequency domain. So first one is the similarly ideal high pass filter, ideal high pass, after ideal high pass filter. Next one is the Butterworth high pass filter. Next one Gaussian high pass filter. Here also, so just imagine there is a reverse process of the image smoothing. What is that? Ideal low pass filter, ideal Butterworth high pass filter, Gaussian high pass filter. Just reverse process of those is nothing but here. Okay, ideal high pass filter. So consider this one. This is the transfer function. H of u comma v is equal to 0. So d of u comma v less than or equal to d naught. 1 for d of u comma v greater than d naught. Here d of u comma v is the distance from u comma v to the center of the mask. So just to see here at origin high here. So observe this one. So that has the 0 at origin. So as uv increases, the value is high. H of u comma v value is high. So see this. Now this is the one image for the ideal high pass filter. So at the center here blackness is there. So here is a white. That means that there is a sudden transition from this value to this value. See this. So observe the characteristic curve also. Okay, this is the D naught, right? D naught. So now up to D naught 0. Beyond the D naught the value is at high. Okay, 1. So now Butterworth high pass filter. So Butterworth high pass filter transfer function is 1 by 1 plus d naught by d of u comma v whole power 2n. So these are the graphs here. Okay, this is the image and this is the representation of the particular image. What is that in 3D plot? And then this is nothing but characteristic between h of u comma v and d of u comma v. Okay, now for order different n values. So you here you just plot like this different what is that lines. Okay, so okay. Now coming to the Gaussian low pass high pass filter. So here the transfer function is h of u comma v is equal to 1 minus e power minus d square of u comma v by 2 d naught square. Now same thing. So just reverse of a Gaussian low pass filter. Now here is nothing but this is the one graph. Okay, now here same thing spatial response of the Gaussian high pass filter. So see this, there are no ripples here. So just observe this one. Okay, right. So now coming to the here spatial responses of high pass filters. So if I observe ideal case, if I observe the ideal, so see the graph. So ripples are there. Here is the one for Butterworth. So right, less number of ripples for the order of that depends on the n value order of the filter. Okay, it's okay. Now coming to this Gaussian case, there are no ripples. Okay, right. So okay, now coming to the results here. So take the same image. So sharpening means you know that a sharpening means you just highlight the transitions, sudden transitions. So in such a way you can reduce the blurriness. Okay, right. So now here see this edges are highlighted. Okay. So now results of ideal high pass filtering the image in figure A with the D naught 15, 30, 80 respectively. Okay, 15, 30, 80. Okay. See here you may observe the ringing effect. Okay, here also ringing effect. Okay. So this that means here this one is an example for the ideal high pass filter, and next one is the Butterworth high pass filter with the rate with the order 2. So that's why here ringing effect is almost neglected. Okay, if order is increased, so of course you can see the ringing effect in this Butterworth high pass filter also. Next coming to the here third case Gaussian high pass filter. So there is no ringing effect. Okay, you can observe the what is that uh, um, highlighting the sudden transitions. See this based on the, what is that, d naught, 15, 30, 80. Okay, right? So for lower d naught values, you can sharpen the image with more effect. Okay, right. Now coming to the next one. Up to now have completed what is that, low pass filters, different low pass filters and different high pass filters. That is nothing but image smoothing and image sharpening techniques in frequency domain. Now coming to the another topic here, that is nothing but homomorphic filtering. Homomorphic filtering. So, okay, here homomorphic filtering means, first of all, you should concentrate on image formation model already discussed in the first unit. You know that f of x comma y, the original image, is nothing but the product of two components, I of x comma y and r of x comma y. So, okay, I of x comma y is the illumination, r of x comma y is the reflectance. So this illumination is determined by the illumination source, and this reflectance is determined by the characteristics of the imaged objects. Okay, already discussed in the first unit. And then of course you know that f of x comma y is the I of x comma y into r of x comma y, and what is the range of I and what is the range of r. Okay, so of course you know that. Now coming to this one, homomorphic filtering. So homomorphic filtering means, so here in some images, the quality of the image has reduced because of non-uniform illumination. Okay, so non-uniform illumination means, that means here, at one in whole image you can get the high illumination at one side, and the another one low illumination also. That means the light effect is that means varied here. Here suppose one shadow is there, so the light is falling on one object, so right, that object shadow is appeared in the particular image. Okay, we will see that one clearly. So that is a non-uniform illumination. So here homomorphic filtering can be used to perform illumination correction, right? So here this is the equation. So it cannot be used directly in order to operate separately on the frequency components of illumination and reflectance. Okay, right. So that's why here we may use the here another equation instead of this equation. So here if I take this equation, so here I cannot separate the illumination from the reflectance. Am I correct? So that's why here I just, okay ma,